Welcome, my dear student. Myself, Sjctnc-Differential, Assistant Professor, Department of Mathematics, Sjctnc-Academy. This is the video for differential geometry. It is an Unit 2 Part 2 video. Part 1 video is seen tangent plane, tangent surfaces, and fundamental existence theorem for space. It is in continuation of last video. In this video, we are going to see the following one. First one is helix, second one is the metric surfaces, and the problems based on helixes and metric surfaces. First, helix. In helix, first we are going to see the cylindrical helix. The cylindrical helix is a space curve which lies on a cylinder and cuts the generator at a constant angle. The tangent to a helix make a constant angle alpha with a fixed direction. This fixed line is also known as axis of the helix. Now we are going to derive some properties of helix. The first statement: for all helices, curvature bears a constant ratio with the torsion. So the statement says that kappa by tau is a constant. That is what the statement says. We know curvature is kappa and torsion is tau. So now we are going to prove kappa by tau is constant. Here let us assume that the curve be a helix. We are going to prove kappa by tau equal to constant at all points. By the definition of the helix, let A vector be a constant vector and parallel to the generator of the cylinder, and T cap be the unit tangent vector of the helix. Again, by the definition of helix, the tangent to a helix makes a constant angle alpha with the fixed direction A vector. So therefore we can write T cap dot A vector equal to, by the definition of dot product, mod T cap mod A vector into cos alpha. T cap is a unit vector. So therefore we may write T cap dot A vector equal to A cos alpha, because mod T cap is 1, mod A vector is A. Now we are going to differentiate this one with respect to S. So therefore we write d by ds of T cap dot A equal to 0, because here parameters S, cos alpha is a constant. So we will expand this one, T cap dash dot A vector plus T cap dot 0 equal to 0. By the Sjctnc-Differential formula, we may write T dash equal to kappa n dot A vector equal to 0. So we take kappa as constant outside, therefore we may write n cap dot A vector equal to 0. So this implies that n cap dot A vector equal to 0. So we know any two dot product of vectors equal to 0 means these vectors are perpendicular. Therefore we can say that A vector is perpendicular to n cap. But A vector denotes the constant vector parallel to the generator of the cylinder. So which implies that A vector is and all the generator are perpendicular to n cap, which implies A vector must lie on the rectifying plane. So by the definition of the rectifying plane, we can write A vector equal to T cap cos alpha plus B cap sin alpha. Now we are going to differentiate this equation. So we will get dA vector by ds equal to T dash cos alpha plus 0 plus B dash sin alpha plus 0. So therefore we write 0 vector equal to T dash by Sjctnc-Differential formula, we may write kappa n cos alpha. B dash is by Sjctnc-Differential formula minus tau n sin alpha. So we take n as outside. So kappa cos alpha minus tau sin alpha into n cap. So which implies that kappa cos alpha minus tau sin alpha and n cap equal to 0. So we need dot product on n cap on both sides. So you will get kappa cos alpha minus tau sin alpha equal to 0, which implies kappa cos alpha equal to tau sin alpha, which gives kappa by tau equal to sin alpha by cos alpha. That is kappa by tau equal to tan alpha. That is, we say that kappa by tau is a constant. Conversely, we are going to prove, we assume that kappa by tau is a constant and we are going to prove the curve is a helix. That is, we assume that kappa by tau is a constant. So let kappa by tau equal to c. So which implies that kappa equal to c tau. We know that the certain formula t dash equal to kappa n and b dash equal to minus tau e. Without loss of generality, we may multiply this b dash with the c vector on both sides. So therefore, it gives c b dash equal to minus tau c n cap. Now we are adding these two equations. We will get t dash plus c p dash equal to kappa n minus tau c. So n is common, we take outside kappa minus tau c into n cap. By equation 1, we know that kappa by tau equal to c by our hypothesis. So therefore, tau c minus tau c into n cap. So which is 0. This implies that d by ds of t cap plus c b cap equal to 0 vector. That is, t cap plus c b cap is a constant vector. That is, we may write the t cap plus c b cap equal to a vector. Taking dot product of each side by t cap, so we can get t cap dot t vector plus c into b cap equal to t cap dot a vector. T vector dot t vector is value is 1, t vector dot b vector value is 0. So which implies that t cap dot a vector is equal to 1. So that is, t cap dot a vector is a constant. So if the angle between t cap and a vector is alpha, then the tangent makes a constant angle with a fixed direction a cap. That is, the curve is a helix. So which clearly says that the curve is a helix. So from this idea, we can immediately say any helices kappa by tau is a constant. Next, circular helix. A helix lies on the surface of a circular cylinder is called a circular helix, and the axis of the helix is the axis of the cylinder. If z-axis is the axis of the helix, the parametric equation of the curve are x equal to a cos u, y equal to b sin u, and z equal to b, where a is greater than 0. If b is greater than 0, the helix is right-handed. If b is less than 0, the helix is left-handed. So now we are going to solve some problems. The first problem, if C represents any general helix and the plane C1 represents the projection of C or a plane orthogonal to its axis, then prove that kappa equal to kappa 1 sin square alpha. So now we are going to prove. So it clearly says by this diagram, OP vector equal to OP1 vector plus P1P vector. That is, R vector equal to R1 vector plus P1P vector. If A vector being unit tangent vector, direction of generator P1P vector is parallel to A cap. So if we write that P1P equal to OP cos theta, that theta is the angle between R vector and the A vector. But A cap dot R vector equal to A cap dot OP vector. By the dot product, we may write mod A cap mod OP vector into cos theta. That is, A cap dot R vector equal to P1 P that is OP vector into cos theta, as we may write P1P. So P1P vector equal to mod P1P vector into A cap by unit vector. So therefore P1P vector equal to mod A vector dot R, A cap dot R vector into A cap. Now you substitute this value in equation 1, we will get R vector equal to R1 vector plus A cap dot R vector dot A vector. Now differentiation with respect to S, we get dr by ds equal to dr1 vector by ds plus A cap dot dr by ds plus ta vector by ds into R vector into A vector plus mod A cap dot R vector into dA vector by ds. That is R dash equal to dr1 vector by ds1 into ds1 by ds, because now we change parameter in terms of R. So A vector dot R dash is we write t, dA by ds value 0, and A vector dot R vector into dA by ds value is A vector. So this is we write R dash is t. So this is we write R1 dash t R1 by S1 as R1 dash, and second one is we take as it is ds1 by ds plus A dot t into A cap. This is 0 and this is also equal to 0. So therefore we write t cap equal to ts1 by ts into t1 cap plus A dot t into A cap. Taking dot product on each side by t1 cap, we get t1 dot t equal to ds1 by ds into t1 dot t1 plus A dot t into t1 dot t. So we get this value is 0, second term is 0, only first term will be equal to 1. So therefore t1 cap dot t cap equal to ds1 by ds. Again, by using this figure, we may write this one mod t1 cap into mod t equal to sin alpha, which is equal to ds1 by ds. And we substituting this equation in 5, t cap equal to sin alpha t1 plus A cap of t cap into A cap. And t cap equal to sin alpha into t1 cap plus cos alpha into A cap. Again we differentiate with respect to S, dt cap by ds equal to sin alpha into dt1 by ds. t1 equal to sin alpha into dt1 by ds into ds1 by ds. That is equal to sin alpha into ds1 by ds into t1. That is t dash equal to sin alpha into, we substitute this value in this equation. Therefore sin alpha into kappa 1 into the t1 dashes, we write kappa 1 tn. That is we may write kappa n, t dash by Sjctnc-Differential formula we write kappa n. So therefore we write as kappa n cap equal to kappa 1 sin square alpha into n. So kappa equal to kappa 1 into sin square alpha. Also the normal of C1 is parallel to the principal normal of the helix at the corresponding point. So that is the proof for this problem. The next problem is, if the curvature and torsion of the curve are both constant, then the curve is a circular helix. So let us take C be a given space curve, and given that kappa and tau are constant. Already we know that kappa by tau is a constant, the curve is a helix. So therefore it lies in a circular helix. Thank you.